Thank you for coming. So this talk is about the minimum description length, where MDL is the minimum description of minimum description length. And it's about sort of extending the classical results in MDL to the singular setting. So if you look through the literature of MDL, there is like a lot of statistics. There is this implicit assumption of regularity that sort of pervades the entire literature, except for one paragraph in Grunwald 700-page book that reference Watanabe. So this is sort of a preliminary work to extend the formalism to singular models as we are researching. So this talk has two parts. The first part is going to be theoretical, so it's going to be the boring part, and then the second part is going to be Einar presenting pretty graphs.
Go theory.
Go theory, yeah. I mean, this is a conference for nerds, right? Yeah. All right. So the main philosophical frame, as a lot of people know, is this principle of parsimony, simplicity bias, and choose the simplest explanation that fits the data. And this is a very, very old sort of philosophical mindset. You can see. So this is a quote from Principia by Newton. There's that true and sufficient. So the fitting and like the just enough. And then there's this like often quoted like entities should not be multiplied beyond necessity, like attributed to William of Ockham, so Ockham's razor, that I think it's paraphrased multiple times, and I asked GPT-5 to like trace, and it's like unclear who said what, but it's a pervasive thing, and multiple theologians like this principle. Right, so this is another frame that I think is pretty important and maybe underemphasized in the current literature, which is the frame of communication. So like Shannon's information theory, since the very pivotal seminal paper by Claude Shannon, it's the fact that you have a sender and a receiver. We typically call them A and B, or Alice and Bob. That has a message the sender wants to send, and then there's a communication channel. We throughout this talk we'll assume that this is a lossless, non-noisy communication channel, and then there's an encoding of the message, let's say in binary, sent through the channel, and then Bob will receive that message and decode it, and hopefully the decoding is not lossy, and hopefully you get the same message back. So if you scramble this and you get like singular MDL, so if Alice frame of Bob is that, hey, that's someone who attend ILIAD, send over this string. Well, I think the first guess would be singular model, but then maybe the second guess would be singular MDL. So this is tying together a few points, which is communication includes this guessing and probability and also knowing what shared information there are between the sender and receiver. And those are important things to keep in mind as you develop the theory. Okay, so quick run through the background of classic MDL. So the minimum description length as a principle is an incarnation of the Occam's razor within statistical modeling. There's like earlier work by a lot of people in this conference will be familiar. Earlier work that predates, I think, MDL by Solomonov, Komogorov, Kaitin, that sort of formalize the problem of inductive inference and implement this idea of you inductively infer the underlying explanation that fits all the data, but also the simplest. And this is sort of we nowadays we call that algorithmic information theory, or AIT, and I think a lot of people in this conference will be interested in the subsequent work by, for example, Marcus Harder and Shane Lake, that uses this idea to build sort of idealized agents out of it. But following that, sort of Risanen, Clark and Barron and others sort of gave a computable treatment. So AITs are frequently about Kolmogorov complexity and things like that. That is not computable. But if you sort of restrict the space of programs that you search over to this statistical model, restrict that by using a statistical model, you get sort of a computable treatment, but like less powerful, but also directly related to the problem of statistical modeling and modeling random data that scientists of the day cares about. Right. So in 2007, there's this big book by Peter Grunwald. So why study MDL for us? So it is sort of about model selection. So model selection is again that frame of among the model that fit your data, which one should you choose, and simplicity bias and an understanding of how model generalize. And this is kind of emphasized by that, for example, Dan's talk, understanding how model generalize either in distribution, out of distribution, with distribution shift. These are important points to understand how understand sort of boundaries and safety characteristics of our models. I do want to admit, or at least say that the theoretical work here is, I think, compared to a lot of work that you have seen, is a little bit more blue sky. So in the sense that the point is kind of almost not the results, but the objects, understanding the intermediate objects. Okay, quickly go through some definition and assumptions. These assumptions, like most of the assumptions you see in SRT and in physics, are usually sort of sufficient but not necessary, and then finding the necessary conditions are sort of case until someone sort of generalize everything. Okay, so the outcome space, the space of samples, or the space of things that the sender would like to communicate. I'll denote that as like X, curly X, is a finite set of symbols, or in modern LLM we call them tokens. A data sequence of length n is always going to be the data set size, is an element in X to the n, and drawn from some data distribution Qn, which is, so the delta is like the simplex over X to the n, or the space of probability distribution over X to the n. So I'm going to, right, so why do I have this superscript symbol? Just to call out that I'm not assuming IID here. If I do assume IID, like the data distribution being IID means that it factorizes this Q to the n factorized for some fixed Q. That is a distribution on the non-product space, the base token space. And I'll frequently use the abuse notation and like this base thing, and then evaluate it on a sequence of that means this factorization, this product form, and when that's when IID is in play. Okay, and the other component is a finite dimensional model. So by a model, I don't mean a trained LLM model. I mean a parameterized family of probability distribution, P star W being the weight or the parameter, capital W being the parameter space. So if there's an IID assumption where I say that the model is IID, the same intentional abuse happens. Just a moment. I do want to sort of emphasize the fact that you can have an IID model modeling a non-IID data source. or vice versa. Right. So, yes.
Just quickly, when you say dimension, do you mean that the cardinality of M is finite?
No. Right. So typically in this talk, I will assume a finite dimensional model, meaning W is a subset of R to the D for some finite D. Okay. We will encounter this like finiteness thing later. I think you first.
I was just going to ask, is this X, is weight X the same as curly X?
Thank you. That's curly X. Yeah. Yes.
So when the model is IID, does it mean that the weights are independently sampled?
Oh no. It means like, so if I want to model a data sequence like
Right.
X to the n, the type signature of this should be a distribution over like
But you
over
said
this.
that an IID model could model a non-IID.
Yeah. So if I have a data sequence x1 xn, I can, so regardless of whether or not this thing is drawn IID from a fixed Q, each xi is drawn from a Q, or the entire thing is drawn from Q or Q to the n.
Yeah.
I can always still say that I have an IID model that such that I'm basically constructing P to the n, defining for every n of x1 xn to be equal to the product for a fixed PW.
The same PW for each XI.
Yes, the same PW for each xi.
Okay, but if the model is IID and the data isn't, the model will be wrong?
The model would be wrong.
Okay.
Most models are wrong. Yeah.
Okay, but then it wouldn't be a model of the data, it would be like...
So, like the LLM transformers likely does not contain the likely does not contain for any weight of the model. Likely does not contain
Right.
the actual distribution of
Okay.
of the power, for example. Yes.
How can an object of this type capture correlations between things? So it looks like you've just written down
Right.
IID model.
Which yeah. So this I'm usually assuming an ID. Yeah. We'll see more. Right. So finite dimension compact. I'll assume compact d-dimensional parameter space and non-empty interior, just to have no sort of collapse degeneracy. That's a little bit. Okay. Example, which will probably clear out a lot of those. Let's say. Wait, I didn't. So this is like a say language model or sequence model example. So the X will be token space or vocab space. Llama is like 50,000 tokens. The data will be a text corpus or a mixture of text corpora like the PAL. Model will be an autoregressive sequence model, for example, transformers. By that I mean for any sequence. Oh, sorry, that should be L. So if L is the context length. We learned little p sub w, and then for every sequence of length L, the joint distribution is defined in autoregressive manner like that. Okay, this is a sidebar discussing this IID point, which is about LLM training. So language is not IID, otherwise there will be no structure left to learn. Right, that probably is the answer that you are seeking. So during pre-training, so what should the X be? What should the sample space be? I will argue that it is like more realistic to say that it is like vocab to the context length, to the max context length. And the data set is like chunks of these contexts, right? Then if the training process is like taking random sample of this max context length string, then that is right. Then we are learning joint distribution, learning a distribution over this individual samples of strings of size L. I think there is like other like more realistic assumption that can go into here. So there's this idea of global batch size. So in typical LLM training, you have the data loader that like grab things from the PAL or grab things from your corpus. So here, in a typical batch, like the each individual rows of the batch is also correlated, right? They are usually sort of chunked from a single document. So you have this like global batch size. So for example, in Llama training, this is like 4 million token or 16 million token, and Llama 2 and Llama 4, and that can change over training. So it's a bit of a messy situation. So it depends on how you load data, how you collate the batches. So that's a sidebar. Okay. So this is to also preempt a potential question to Einar's language model, like how can you do non-IID thing on the IID theory? But if you look at the actual training and experiments, they are usually at this level. Yes.
So what I feel like you're saying on this slide is basically like, okay, by doing all of these considerations, we get something that's like, if you squint, it's like almost exchangeable. And then
almost exchangeable. Yeah.
And then when you have a lot of data, exchangeable is like almost IID.
Yeah.
Okay.
Yeah. Yeah.
What is exchangeable?
The order of the samples doesn't matter.
The things that allows you to use the conclusion of what you derive from IID. Yeah. Okay. So this is I'm going to go through. I'm not going through the things like Kraft Macmillan or things like that. I'm going to just say that there exists a correspondence between code. You have a sample space. If you have a distribution over the sample space, then that means that almost uniquely defines a code over the symbols in that space, and then that code is unique. You can uniquely map symbols to code, and then you can uniquely map code to symbols, so encode, decode. So this is an example. So if you want to communicate with someone in San Francisco, is pretty sunny. So we are in San Francisco. In California. Sorry. That's Berkeley. So sunny, cloudy, rainy, and then you have this sequence of observation. This is, say, the observed distribution, and this is a distribution over this symbol space. You can build a Huffman code where the most likely, most probable symbol gets shortest code. And compared to a naive code, which is a uniform distribution over these symbols, the top one will be the code for this set of things, and the bottom one is a shorter code. So the key theorem here is Kraft-Macmillan. Not only do you have this like almost one-to-one distribution to code correspondence, the main thing to say is that the length of the code is given by log of surprise, and surprise is 1/p, or negative log of p, negative log of the probability. Right. So using the example of like sending over singular ends. Okay, we'll get that. Okay, so for us machine learning people, there is this pervasive principle of like learning as compression. Compression is learning. So the broad idea here is that a simple hypothesis or a data set with some with less that you can compress means that it has pattern that you can exploit. So for example, you can always like instead of sending this string, you can say just write 1,000 zeros, send the instruction. You can instead of sending singular and minimum description length, you can send this string and say your second guess, and all lowercase. The first case might be singular model, depending on the shared knowledge. So instead of sending this huge string, which is like 65 kilobytes or something, you can say Google chapter 1 of Adventure of Sherlock Holmes. So that is another thing that depends on the shared knowledge between the sender and receiver. Because Google has already arranged the shared entropy in the environment out there in the world. And LLM so this is a more direct illustration of that principle, which is that LLM is a general purpose compressor. So let's say, for example, Alice and Bob both have access to Chinchilla 70B. I don't think anyone, it's not open source, right? Let's say it is. So you can construct an auto-regressive, and in MDR it's called prequential or predictive plus sequential encoding decoding scheme. You can start with a prior over over a token, encode the first symbol with that prior. Remember that any distribution determines an encoding, and then do this autoregressive encoding, and then like Bob would receive the first I symbol, then he can construct this. If PW is shared, meaning a shared chinchilla, then Bob will already have these, so he can construct this, and therefore construct code, and therefore decode XI. Yes?
Why do you need a prior? Why can't you just encode X1 with the model's distribution given no context?
Yeah, you can choose that. That is a prior. That is a distribution over, okay, just start with any distribution you want, right? Uniform is fine as well. And the total code length is then, remember that is given by log of 1 over surprise and sum over those sequences. And just noticing that this is the same as a cross-entropy loss, which means that when you train LLM, you are literally minimizing description length. And then you are trying to find a minimum description length. This is actually, someone actually do this. I chose Chinchilla because there is this paper, somewhat recent, from GDM. And Chinchilla 70B, if both sender and receiver have the model already, so the model is a shared knowledge, then they can use this variation of this encoding scheme to encode text. So Chinchilla is trained on text, yeah. And you get that Chinchilla 70B beats the usual sort of model agnostic text compressor out there. The surprising thing is that even though Chinchilla is trained on text, it also beats other image and speech domain-specific compressor, like.
So you just feed the pixels into Chinchilla as tokens?
Yeah, you feed the pixel into tokens, and then it still beats them, right? So this is like, there are patterns, and a common pattern, like I wouldn't be surprised if induction is a pattern in text and obviously speech, right? Speech and text. Right, but if you include the fact that if you don't have this shared model, if the sender and receiver doesn't share Chinchilla, then you need to also send Chinchilla over, right? Then, well, you don't beat it, obviously. Well, no, it is not obvious, but so it's not. I think I didn't pull out the number, but you will still beat it if this sequence is like ridiculously long, like if the things that you want to send is very, very long, right? Yes.
In this like graph, is the Chinchilla compression rate like? Is there some method of like if we both have Chinchilla, I can send you a lossless encoding, or is it like also?
Yeah.
Okay, there's okay.
Yeah. Cool. So I'm going to quickly go through how people measure code performance, like a performance measure. So every time I see code, I say code, you should also think a coding distribution. So those two things are almost one-to-one. So one way to measure performance of particular coding distribution is something called redundancy, which is you compare the code length. So the code performance of a coding distribution P on a particular data sequence X is the difference between the code length and compare it to if you have access to the underlying data distribution. The expected value there is the KR divergence. You also frequently look at minimax expectation. So minimax is, so what if the data distribution is, so you have a two-player game. The player one chooses the data distribution, and then player two wants to minimize code length. So that's the minimax expectation. And then there's regret. So instead of comparing to the underlying data distribution, you compare it to the best in model class. Okay. Right. So I'm going to introduce two common coding distribution. One is two-part code. So in two-part code, so it's two-part because the message that Alice sent to Bob is going to contain two parts, and that's going to mirror our chinchilla story earlier. So Alice and Bob only share the model architecture. It shares the chinchilla architecture. That's a shared knowledge. They share the code construction recipe. So given any distribution, I say the distribution and code is almost the same. You need to make a bunch of the, choices to make them actually one-to-one. And then a way to communicate. So this model, given a chinchilla architecture, that is a family, a parameterized family of hypotheses of distribution. You need a way to communicate that. For example, send over the weights. And then finally, you this is maybe not very important, which is like everything here is like related to n. But if they don't already share knowing what the length of data is, you can always just pay log n to send over that number. Right, so for communication, Alice observes data. Alice will try to find a good encoding, for example, train chinchilla on that data, and then communicate the trained weight, and then use that train distribution to encode. Good here means, for two-part codes, minimizing the sum. So two parts of the message, you need to send the weights, and then you need to send the encoding of the data relative to the weight. Okay, sorry. So that's two-part code. The other code is, okay, that's a way of communication. The other communication method is Bayesian code. Here, okay, here's where the theory is actually easier. Right, let's do that again. So share architecture, share model, code construction recipe. But then now, a Bayesian code is pinned down once you choose a prior over the distribution in model, or choose a prior over, since we have parameters, it's a prior over the weights. So for communication, again, observe some data sequence, and then you compute this distribution. And this distribution is just a prior mixture over the model likelihood. And if you screen and that is just the evidence, the partition function / the marginal likelihood, or Zn that you see in SLT everywhere. That is the normalizing constant of the posterior. I claim that it is a likelihood. You can just compute. If you integrate over xn, it integrates to 1 straightforwardly. And then you use that to encode these things, encode the sequences. Well, Bob also have access to, that is shared, right? Has access to the prior. So he can create exactly the same distribution. He doesn't know which xn, but then he can construct the code and then decode whatever is sent that is encoded using that. The code length then is negative log of this thing, which is called the free energy that you see everywhere. Or in MDL it's called stochastic complexity. Okay, the classic result is that if you have a d-dimensional IID, this is the only place where IID goes in. The whole setup doesn't require IID, but like when you need, when we talk about asymptotic expansion, IID comes in. If you have a regular d-dimensional model and IID data distribution, that is realizable, so Q, the data distribution, is part of the model. And if we use two-part code to encode the data sequence, or Bayesian code, actually a lot of other codes, there's no maximum likelihood code, like a lot of code, then every performance measure that I was talking about, expected regret, expected redundancy, minimax redundancy, all of that, is asymptotically given by d onto log n. That's a very familiar result, or that's the Bayesian information criterion penalty, the Dion to Logan penalty. Right. So this is true for all reasonable data distributions. So like not realizable is also fine. And so that and there is no, so when we talk about model selection, this is the penalty for not having the weights. That is the simplicity of the model, simplicity of the weights. That's the penalty. So there's no way to select model based on that criterion within one single family. You just need to select over architectures. Except you can do selection at the low order terms. And in the specifically for the base code, the low order term is given by this log of the denominator of the Jeffreys prior. So that's the minimax result. Okay, so when we switch to singular model, a bunch of things breaks. So in singular model, you don't have identifiability. So recall the definition. The definition is like a regular model is one where every parameter codes the same distribution. That's just not true in transformers or neural network or any model worth the name machine learning model. And it has degenerate Fisher information matrix. So locally, how the model changes with weights is not a metric. It's not characterized by a sort of second order characterization is not sufficient. And then lots of technical tool that allows for the results that we see breaks. So for example, there's like this non-locality in parameter space. You can't just, when you look at a particular parameter, you can't just, when you look at a particular hypothesis, you can't just use differential geometry at the parameter that parameterizes that particular model, right? And so if it is localized, then you can do calculus near that. But for singular model, this particular hypothesis is parameterized by an extended object, and different neighborhoods of that extended object acts differently. This is a technical thing. The KL divergence in the regular case is symmetric locally, because it just becomes the Fisher information metric interpreted as a metric. And in single model, the local geometry is like more complicated than just like balls. Okay, but I think more fundamentally there is like issues, more fundamental issues that is a theme throughout the talks in SLT, probably not in the past couple of days, but for talks tomorrow and moving forwards, is this kind of program as singularities philosophy, not to speak. Like there are many evidence, but go to Will's Troiani's talk and talk to Dan, talk to Zach, talk to me, and this realization I also found it in just Resonance paper, the originator of MDL, that so in that paper assumes regularity, but then so a regularity is like an assumption that goes into the paper, because if you don't have that, then you get this quote. So what makes this phenomenon, there's a phenomenon in which if you don't have regularity, something blows up. Particularly unpleasant is that it tends to happen for strings, for things you want to compress, that have strong statistical regularities that permits a shorter encoding than you expect. Right, so here's a very old realization of this. So it's not like a singularity is a unknown thing. It's just we don't have the tools to deal with that then. So I mentioned that to extend the result to singular case, one of the easiest thing to do is in the Bayesian code case, which is that, hey, the code length, what is the code length? It's the free energy. And Watanabe gave us the exact free energy formula, the expansion, which is given by this. So for Bayesian code, the redundancy is given by, so redundancy is code length minus the length if you encode it with the true data distribution. which is the entropy of that distribution. This is empirical entropy, and it expands like that. That's the familiar free energy formula. So what about minimax result? The result that sort of the singular version for Jeffreys prior, for example. Well, so I look into that particular problem. So here's a partial result, which is that if you, I'm not going to talk about this much because if you're interested, ask me about it. But if you define things like this, so define this quantity, which looks like some sort of tempered distribution, and then there's a beta. So instead of having a Jeffreys prior, you have sort of a family of prior where, depending on the number of data set that you want to encode, you define things that way, and then you have 1 over z of w, and then you have this normalizing constant. Then, given some assumption that is similar to what SLT have, then you get the minimax result is you have the expected redundancy being less than log of that thing. So it's like the volume of the hypothesis space at the level of resolution permitted by n.
You are at 25 minutes.
Cool, thank you. Right, so, and furthermore, this log n expand like this, where instead of lambda, so this is a minimax result, right? So if your adversary can choose the worst possible distribution for you to compress, data distribution for you to compress, and you get the worst possible result. Yeah.
Is Vn like a epsilon ball around the hypothesis that like shrinks with n? Is that the idea?
It's more about sort of a global volume of the hypothesis space. So I meant, yeah.
Yeah, I can ask you later.
Yeah. Okay, so to connect back to more practical things, let's use the two-part code formalism to talk about model complexion, like neural network weight compression, which will connect back to what Einar will present. So recall that to communicate, we need to communicate the weight, a chosen hypothesis in the model that minimize this two-part objective function. So for a finite dimensional parameterized model, we can communicate that the hypothesis chosen used by communicating the parameter. But here's where that finiteness thing come back to bite again. Any encoding scheme, like any encoding scheme where you send bits, at least send bits over to Bob, can only specify at most countably many things. And if your encoding has like finite length, the message always has finite length. That's like a finite set. That you can only communicate finite number of things. So we need discretization, right? So float 64 is already a discretization, for example. But if you have a particular discretization, then you incur some sort of error or excess. So before, if you just choose the best possible hypothesis, but then your best possible hypothesis is not part of these finite things that you can send, then you incur some sort of loss. And that loss is, this is where like a bunch of technical tools or regular models sort of breaks. But you get something that looks like that, which is, so you have sort of per symbol, your discretization, so per symbol, this is n here, so this is per symbol per x excess is given by the KL divergence between Q and the chosen grid point that you send over. So there's a trade-off. The finer, so Flock 64 is like much more expensive, but then you get less per symbol excess. So you need to balance those two things. So let's say we allow for at most epsilon amount of excess. So what does that mean? It means, based on that criterion, it means that sending anything within this set of parameters, sending anything in here within this set in the parameter space is permissible, because anything in there will incur at most epsilon loss by definition. The cost of communicating any point within a set, in a larger set, is log of the ratio of the volume. Okay, let me denote that communication cost for that parameter as length L. So the access code length is bounded by n times the worst access plus the need to communicate that parameter. Now suppose the volume of this set scales like epsilon to the lambda. Then this little l looks like that. And then if you optimize this quantity, you get that epsilon and the right fine grainness of your grid should be of the order of 1 over n, which is intuitive. The more data you need to send, the more you are willing to pay in terms of accuracy to get a smaller per symbol loss, per symbol excess. Okay, so and if you plug this in, then you get a total excess code length of lambda log n. So this thing will come out again, right? So this is a very obvious thing that you will guess is the final result, right? D on 2 becomes lambda. Sorry, did I say lambda is the RLCT or LLC? Yeah. Okay, so I'm going to, so this is just a graph of the tolerance epsilon against that. This is a theoretical graph. And then sort of difference between regular and singular models. Right, so now Einar is going to present, sorry, what is the time? Any question before I hand off to Einar? Okay, I think any question, ask me afterwards. Okay, so I'll hand it to Einar to talk about what that means for model compression.
Cool, thanks. So in order to check whether this holds up in language models in practice, we did some experiments. So one of the experiments we did was that we quantized language models. We did a symmetric and uniform quantization. So it might be easiest to just look at like the figure over here. So you just like set all your weights to a grid where which is symmetric around 0 up to some maximum value. So for instance, for this grid here, there are 7 grid points. So this requires 3 bits to encode the weights here. And then if your weight was like initially outside your maximum value, you just clamp it to there. And if your weight was, say, here, you just move it to the nearest grid point when you do your quantization. Now, the maximal value here, you can set in a few different ways. So we tried setting the maximal value by optimizing for as low loss as possible. So you just like search over maximal quantization values. So you, while you fix the number of quantization values, then we looked at the loss increase of language models. So these are the Pythia models at different sizes. So 160 million, 410 million, up to 6.9 billion. And we looked at how much does the loss increase when you quantize to a different number of bits. And the different colors here are different checkpoints during training. And you can see that they all have like pretty much the same shape. So, and of course, the fewer bits you use, the higher the loss. Yeah.
Why are there more than one dot in between 2 and 4 on the x-axis?
Sorry, why are there more than one? Because we. So this is so we quantize to we quantize to NQ that can be any number, but then when you take log 2 of that, you get the bits. So we allow for non-integer number of bits. Of course, if you want to realize this in practice in an efficient way, you would want an integer number of bits. But since we want to see how this scales, we allow for non-integer bits. Yeah, okay. So you can then define some loss tolerance. We found in practice that this doesn't matter, but we chose a loss tolerance of 0.5. And we then plot how much can you quantize your model, so how many bits do you need to stay within a loss tolerance of 0.5. And what we find is that if you plot that against the LLC, so here, against the estimated local learning coefficient, you find that for many of the checkpoints, there's a linear relation between the number of bits needed and the local learning coefficient, the estimated local learning coefficient. And this linear relation doesn't just hold for these larger Pythia models. We also tried it for smaller Pythia models, and we find ranges of checkpoints for which this also holds for those smaller Pythia models. We then tried a different form of quantization where we just like set the maximal value to just the maximal parameter value of the model. So like now you don't get any clamping business where you need to move your largest parameter into the grid, because the grid is like large enough that you're always just moving stuff within the grid. Of course, now since we don't optimize for low loss, you see that you can quantize much less. So like this graph starts to go up at a much higher number of bits. But we still get a somewhat linear relationship between the LC and the number of bits needed, although not as linear as before. So the R squared of the linear fit is worse.
Yeah. Also to clarify, the theory will predict that the LLC to the bits required is linear to leading order. So we've no idea about the sub-leading terms, and the LLC is estimated.
Yes. So there's like a lot of things that can go wrong here and cause this not to be linear, and we find it pretty remarkable that it is as linear as it is, at least for certain checkpoints. Then there are some checkpoints when our LLC estimates go ballistic, which we don't know why. So there might be an issue with the LLC, or it might be an issue with other terms that become important. Yeah.
Those checkpoints that are just so far from the linear fit, are they like earlier checkpoints or later checkpoints?
They are both earlier and later checkpoints. So the checkpoints start here, and then it might actually be easier to see in this figure here, for instance. So the checkpoints start here, and then these are the latest checkpoints.
Yeah. Okay.
So yeah, so you get that basically both early and late you have a divergence from the linear fit, and the same thing here. You see many of the earliest checkpoints don't fit that well. Yeah. We also tried a different compression method, which is the matrix factorization. So since the weight matrices of a language model are, well, matrices of numbers, you can compress them by doing SVD. So you just like make your matrix into a product of two smaller matrices, and thereby force it to be lower rank. But this can save you some model parameters, because if your matrix initially was like D1 by D2, then after compression, your matrices are like D1 by some n, and n by D2, and if n is much smaller than D1 and D2, you have saved like quite a bit of space. So in the plot I'm about to show now, the what I call the compression fraction is just the number of parameters after factorization divided by the number of parameters before factorization. Yeah. So then you get this thing here. So this is how the loss increases as you compress more, and we don't find a neat linear relationship, or it is not as linear relationship as we found with quantization. Now, the way we do the SVD factorization here is that we only target certain layers, which might have to do with why we don't get a neat linear fit, but we are not sure about that. But we do find something that is mostly monotonically increasing with the LLC, which is yeah, qualitatively what one would expect from theory. So higher LLC models are less compressible. Yeah.
Did you try for the so you're applying compression only to particular layers within the model in this?
Yeah.
case? Did you try per like restricted LLC for the weights that you're compressing?
No. We did this to only certain layers because the literature said it's better in the sense that you get less of a loss increase. So it's like better to mangle half the layers like a lot than to mangle all the layers a bit.
Yeah.
Yeah. And therefore we mangled half the layers now. Yeah. Yeah, that was it, I think.
Yeah.
Yeah.
Do we have?
We're at 1 minute.
Okay.
Cool.
So I think. Yeah. So I think.
Do I answer?
So it should. Let's just spell out the number of things that could go wrong, which is like LLC is estimated. And also the compression is not that volume thing. If you go through the math, the volume over volume, the ratio of the volume thing, sort of relies, like, that is true if you sort of optimize over all possible sort of encoding scheme so that your point will like lies in a probably very like odd volume. So unlike the regular case, it's just like ball. So grids is fine. So quantization is fine. Like the quantization sort of basis dependent quantization is fine. But for single model, you do not have that. Okay, cool.
Yeah.
Questions?
We have 10 seconds left. So
Yeah.
Yes.
This is a kind of a weird quantization method. A priori, I would expect that the weights for a model are roughly Gaussianly distributed. So you want to have like a tighter grid in the middle and a fatter grid out the outside. More generally, like standard quantization methods like, you know, GGUF or AWG or all these other like wacky quantization methods that people use in practice, it's, you know, Hugging Face. Why not use that versus this like kind of custom quantization that I don't think is done in practice?
Yeah, so we wanted a simple quantization scheme so that it was easier to reason about. So if you introduce a more complicated quantization scheme, there might be other effects that we didn't control and didn't understand.
Okay.
Yeah, mainly that, and also I looked some into using some of these existing packages, and the problem was that like it didn't let me customize as much as I wanted with how much I quantize.
Sure, very coarse grain.
And also like I want, in order to be able to compute the LC, I need to kind of dequantize, or I need a dequantized version of the quantized model, if you get what I mean. So I need a model in like FP32.
You take the model, you quantize back, and you get like a noised version of the original.
Yeah. Yeah. I think though, a lot of those software don't have dequantization stuff because like why would you ever want to
Why would you
dequantize
care?
a quantized
Yeah,
model?
okay.
Yeah. So there were like issues like that caused me to not use
Sure.
it. Yeah, cool.
I think that's the time we
We're
have.
out of time, right?
Okay.